In this last lesson of Unit 9, we're looking at what are the different behaviors that waves do. To start us off, waves are disturbances that travel through a medium from one location to another. Things we've already talked about are that waves have frequency, that's how often they go up and down in one vibration, the number of cycles per second. The period is the time it takes to do that one up and down. The wavelength is the distance from peak to peak, or crest to crest, or trough to trough. The wavelength is the distance that one wave pattern, one complete up and down, takes up. We get the idea of speed, it's how fast it travels. Amplitude is the distance from equilibrium, and energy, well, that one's harder to quantify. Remember that energy is the ability to do work. So this type of energy can transform from type to type. Now it's a disturbance in that this one particle on the string travels up and down and goes through the medium from one location to another. A thing to keep in mind is that the speed of all waves only depends on the medium. The medium itself is stationary. So in this case, the particle might go around in a circle or might vibrate up and down or back and forth. But this one blue particle doesn't travel across the whole ocean. The medium stays still. Now, on the surface of this lake, the waves travel the same speed because it's the same medium. As a result, the ripples are circular in shape, meaning if this is the epicenter, the waves travel out at the same speed in all directions. This is because the water itself is the same depth everywhere. A thing to note here is where the waves overlap. Do you see that the waves overlap and make spots that are a little bit brighter than those around it? Or a little bit darker? Well, that's a result of interference. Interference is when a wave hits another wave and their amplitudes add. In this case, we had done this already with the Slinky lab. Constructive interference would be two waves on the same side, make a larger wave. Destructive interference, well, this is what noise-canceling headphones do. Your incoming sound cancels produced sound by your headphone because they're opposite in amplitude, creating destructive interference. You might have seen this picture in my room. It is up on one of the posters on the back wall. This was a submission to the physics photo contest. And besides the fact that it's a really interesting picture, it does also show constructive and destructive interference, where the wave from this person's thumb and the wave originating from this person's index finger intersect. It has a larger amplitude. Ew. Transverse waves. Gross. To help us understand this constructive and destructive interference a little bit more, let's watch this with water waves. In this experiment, Veritasium is going to study how light going through two little tiny openings interferes with itself. So he'll use a water wave analogy just like we would with sound. Let's check it out.
So what causes that? Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there.
Now, we'll study this in more depth with light in the next unit, but with sound, that means something really interesting. Have you ever been in an auditorium or a big, drafty building and you realize that in some locations sound seems deadened? Well, then, you are standing in one of these, I suppose you could call them nodes, places where the destructive interference between the waves is causing you to have less amplitude and therefore less sound loudness. You can actually replicate this in a classroom, though you and I won't be able to do it together this year, by having two speakers right next to each other playing the same note. If you walk around the room, you'd get a period of loud, then quiet, then loud, then quiet, then loud, and then quiet. You get the pattern. Right. So moving on. Other things that waves do. Waves interfere. They reflect. And a reflection is when a wave hits a matter and bounces off. When that wave is sound, we call that reflection an echo. Now, it's not that other solid physical objects don't reflect. They hit matter and bounce off. But waves do this in a special way, which we'll talk about next unit. So far, waves interfere, they reflect, and they also refract. You and I have talked about this already. We've talked about how when a wave hits a new medium, like going from the rainbow slinky to the metal slinky, it changes its speed and it causes a bending of the wave. For our unit, an additional thing you should keep in mind is that when it changes its speed, it also changes its size. It changes the size or wavelength of the wave, and the frequency stays the same. Like in the case of this straw, we see the bending of the wave. We definitely see that the straw looks broken. But we also see that the color stays the same. Color is proportional to frequency. So if we're both seeing the straw as red, the frequency must still be red, whether the light goes through air, glass, or glass and water. Refraction is why sounds bend away from the ground on warm days and bend towards the ground on cold days, causing it to sound quiet after it snows. Diffraction is another wave property that we'll consider more in the next unit. Diffraction is when a wave hits a material object and it bends around or through it. Guys, I can't emphasize enough that humans cannot do this. Big mechanical objects do not diffract. If I were to find a really tiny opening in the wall, I couldn't run at it with all my might and then spread out circularly throughout the room, but a wave could. That's why when a student is being really loud in the hallway, we all hear it inside our classroom. It explains why you can hear sound around corners. It also explains why you can see edges on shadows. If you're bored at home because coronavirus, look at an object's shadow super closely. You'll see a very solid section, which I believe is called the umbra, but I could be wrong, that's very, very dark, edged by a wavy section, one that's not quite as dark. And that's because the umbra is where the wave is diffracting, but mostly staying in a straight line. And the penumbra, which is not quite as shielded, is where the light is bending around that object. Absorption is when a wave hits a solid object and it transfers all the energy to it. Like when light hits the color black and the material absorbs that energy. Or sound hits this deadening room. In this case, the wave transfers all of the energy to it, usually causing an increase in heat in either the sheet of paper or in the room. In our case, you'd probably be most interested in how the S waves get absorbed by the liquid boundary at the internal of the Earth. With the Earth's core, when the S waves hit the liquid boundary and they can't travel through it, that energy can't just disappear. So the S waves transfer their energy to the liquid core of the Earth. Last one is easy, transmission. This is when a wave goes through matter. And the picture I shared with this one is how ultraviolet rays, and there are multiple types, go through different layers of skin. First off, they get transferred through a vacuum of space till they get to the atmosphere of our Earth. They get transmitted through the regular atmosphere of the Earth. UVB rays get transmitted through the epidermis, but all their energy gets absorbed by the dermis. This can lead to cellular degradation of the dermis in things like sunburns. UVA rays are more energetic and as a result are transmitted through the vacuum, the atmosphere, the epidermis, the dermis, and transfer all the energy to the hypodermis. Notice that UVA rays are more energetic, therefore more likely to cause cellular deformation that can do things like cause cancer in the long run. That's all, folks. We will talk to you tomorrow.